I like the poster. I don't know if you guys saw the poster. So the talk is called Roots of Generalized Eulerian Polynomials. But the poster looks more like a music album cover, like it's roots of something, and so there's this tree with the roots. Really, the roots refers to the roots of polynomials, so maybe it's a little bit less poetic than the poster suggests, but I think it's very interesting. So it happens a lot in combinatorics, the polynomials that seem to be combinatorial objects. It turns out that they have really nice roots. For example, a lot of polynomials in combinatorics only have real roots, which you should realize is a very surprising thing, because generally if you just write down a polynomial at random, then it's probably going to have complex roots. But it happens a lot in combinatorics that a lot of polynomials that we study end up having real roots. And he's going to be talking about some instances of that. So I encourage you to come, as always. Let's get started with the topic of today. So what I wanted to talk about today is symmetric functions. And let me say right away that symmetric functions are a huge, huge topic, and I'm ripping you off by only spending a day or two on this. Really, it would be very easy to spend at least a semester on this. But maybe another thing that I will mention is that one thing that I want to do is give you a little bit of a preview of one of the mini courses that are going to take place in Colombia that I told you about. So one of the speakers there is going to be Untitled Chapter, who's one of the experts in Hopf Algebras and Combinatorics, and he's going to give a week-long course on this stuff. But I want to give you a little bit of an idea of how this works. And let me just say that even outside of Hopf Algebras, symmetric functions are here's a little kind of meta fact that you're not gonna really get to see fully in this class, but I think as you go on in your mathematical career, you'll run into these things. So symmetric functions are really important in several areas of mathematics. And let me just write down some words that maybe right now won't necessarily mean a lot, but hopefully one day you'll see these things, and then you'll remember that I said these words and that they had something to do with what I'm talking about today. So symmetric functions are really crucial in the representation theory of the symmetric group. I talked a little bit about representation theory last semester. And if you want to understand the representation theory of this very important group, the group of permutations, you end up running into symmetric functions in a very natural way. And this also happens when you study the representations of another very important group that we know and love, the general linear group of invertible matrices. Okay? And okay, so that's kind of an appearance in algebra. But then also, these things become very important in algebraic topology and algebraic geometry in the cohomology of flag manifolds. Okay. And again, I don't want to say too much about this except expose you to these words so that you'll recognize them next time that you see them. Okay. But all of these things are very closely connected to symmetric functions. Okay. But let's get a little bit more concrete. So let's talk about the Hopf algebra of symmetric functions, because we already defined it, actually. So we defined the Hopf algebra of symmetric functions as follows. So we said that it had generators indexed by the natural numbers. So we call the generators L0, L1, L2, etc. Now, if I want to define a Hopf algebra, I need a product and a coproduct. And so we said that the product on these guys is what we call the free commutative product. On these LIs. Okay? And remember what that means is that basically when you multiply LIs, they satisfy no relation except for the relation that every pair of L's commutes. So Li Lj is equal to Lj Li. But otherwise, there's no relations between the L's. And that means that the elements of this Hopf algebra are just kind of polynomials in L0, L1, L2, etc. Okay? And so let me actually write that. Maybe I'll give this the name H. And so another way of saying this thing is that H is precisely polynomials in the variables L0, L1, L2, etc. Okay? That's the algebra structure. That's how you multiply here. And then we discussed how we also need a coproduct. And we know that it's enough to define the coproduct on the generators. And we found that the coproduct, or rather we defined the coproduct here to be as follows. Sum from the coproduct of Ln is the sum from k equals 0 to n of Lk tensor Ln minus k. Okay. And then we defined the unit and co-unit, which we always know are kind of trivial, and we did that. And so we call this the Hopf algebra of symmetric functions. Okay. Now let me remind you where we found this, because you might it's been a few weeks, so you might not remember. So we actually ran into this object. It's not that we defined it because we thought it might be interesting. We ran into it when we were studying incidence Hopf algebras of posets. Okay. So this was, when you take a poset, when you take all posets rather than have a bottom and a top element, and we define the product to be just product of posets, and coproduct of a poset to be all the ways of kind of cutting it in the middle, right? So the coproduct of a poset was all the ways of doing a lower interval times an upper interval. And then when we did this for the very special case of linear posets that are just a chain, so remember L0, L1, L2, etc. represent the chains of different lengths. And so what we said is that Ln represented the chain of length n. Okay? And so actually let me draw it like this. Maybe it'll fit better if I do it horizontally, even though well, maybe let me write it over here. So for example, we said that delta of L2, actually L2 represented the poset, the chain of length 2. Okay? And this was basically all the ways of cutting this in half. Okay? So we can either do this tensor this. Okay, so if we cut right here, or we can cut in the middle, and we're going to get this tensor this. And finally, we can cut at the bottom, right? And so we get point tensor the two chain. Okay? So we get these three different terms. And that's our coproduct. Okay? So it's a very natural Hopf algebra. Sometimes people call it the Hopf algebra of rock breaking. I feel like it should be more like stick breaking, okay? Because really what you're doing is you're taking a stick of length n, and the coproduct says what are the ways of cutting it into two pieces, a piece of length k and a piece of length n minus k. Okay? That's the coproduct is breaking the sticks, and the product is just kind of putting them side by side. Okay, so maybe we'll call it, maybe it makes sense to call this the Hopf algebra of stick breaking or breaking sticks. Okay? And so we defined this and we talked about it and we have found the antipode and all these different things. But the one thing that we haven't discussed is the name. And the name seems very strange according to what we've done so far. We're calling it the Hopf algebra of symmetric functions, and you don't see any symmetric functions here, right? And so my goal for today is basically to explain to you what a symmetric function is and why this is called the Hopf algebra of symmetric functions. Okay. So what I want to show you is that this very Hopf algebra arises very naturally in this context. Okay. So that's the plan for today. Okay. So maybe let's go over here and let's define what a symmetric function is. So we're going to start with a bunch of indeterminates. Okay, let me call it bold x, and it's going to be a vector of indeterminates. And this is not terribly important, but I'm going to assume that I have infinitely many variables. Okay. So these are indeterminates. Okay. And now, whenever you have a vector alpha of natural numbers, then you can define a monomial x to the alpha. Okay? And what that's going to do is it's just going to use these as exponents for the variables. Okay? x1 to the alpha 1, x2 to the alpha 2, etc. Okay? And so I'm going to say that a symmetric function is, let's say, over K, some field K. Yep. A variable. Yeah, just you have some variables. You call them x1, x2, x3, etc. So a symmetric function over K is going to be a sum of things like this. It's a function f of x, and it's going to just be some linear combination of things like this. So sum of some linear combination of monomials. Now, such that if you permute variables, you should get the same function back. Okay? So f of x sub sigma 1, x sub sigma of 2, etc. should be the same thing as f of x1, x2, etc. for any permutation. Sigma of the natural numbers. Okay.
Question about this.
Mm-hmm.
So we're assuming we have potentially infinitely many variables.
Right.
Right? Which means if you have a term where x1 shows up to, say, degree 1, does that mean that every variable corresponding to each natural number has to show up in that term degree 1?
So that's absolutely right, and that means that if you're an analyst, you're probably cringing at this moment. this is starting to worry you, because that's absolutely right. If a symmetric function has the term x1, then by symmetry, because this is supposed to be fixed under the relabeling of the variables, if you contain x1, you have to contain x2, you have to contain x3, and so actually you have to contain x1 plus x2 plus x3 plus x4, all of them. Okay, and well, that should, if you're thinking from the point of view of analysis, maybe that starts to worry you. So let's talk about how you address something like that. But actually, before I say that, let me just do some examples so that we can so that we can all be on the same page. Okay, so examples. For example, let's say that you have a symmetric function that has the term x1 squared. Okay, then again, because this is supposed to be fixed under any relabeling of the variables, you have to contain x2 squared. You have to contain x3 squared, etc. Okay, and so that's an example of a symmetric function. Another example, and so we can write the sum over I of xi squared. Another example is to do something like this. Okay, so you'll agree that if you permute, if you change the name of the variables, that's not going to change this expression right here. Okay, and so this deserves to be called a symmetric function. But what does it mean to take this thing and square it? Okay, we're not really thinking of plugging in numbers for xi's and then taking that result and squaring. There would be a lot of issues with convergence. What this means is that you're going to take the expression x1 plus x2 plus x3, etc., and you're going to multiply it by itself formally, okay, as algebraic expressions. Okay? And that's going to give you a well-defined product. What happens when you multiply x1 plus x2 plus x3, blah, 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 times x1 plus x2 plus x3, blah, blah, blah. Basically you get these terms, and you also get the cross terms. And so you get terms like this twice. Right? And this is just when I write this equation, I don't mean that you're supposed to plug in numbers xi's. I mean that this is a formal equality in the ring of formal power series in infinitely many variables. If you compare the coefficient of a certain monomial here and here, they're equal to each other. Okay, so that's symmetric. Another thing that's symmetric is something like this. Right? These are all the ways of writing xa squared xb. And so if you rename all the variables, if you rename the variables in some way, that's not really going to change the expression. Okay? It's also always good to see a non-example. So let me show you a non-example. Sum over the I is less than j of xi squared xj. So why is this not a symmetric function? That's right. And so, for example, let's look at the numbers 2 and 3. So the monomial x2 squared x3 appears here, but the monomial x3 squared x2 does not appear here. Okay? And that's a permutation, the permutation that leaves everything fixed and switches the numbers 2 and 3. And so in a symmetric function, if x2 squared x3 appears, if it's symmetric, x3 squared x2 should also appear. And here it doesn't. Okay? And so this is a non-example. Okay? Okay, so let's let SF represent symmetric functions. Over K, let's say. Now, actually, I call it, it's more customary to call it sim. So sim by definition is going to be this. And I should say that later on in life you might want to take, instead of a field here, you might want to take a ring, and this also works. But let's keep it simple today and just do this over a field. Okay? Okay, this is an algebra class, and so whenever we define a set, one thing that we should wonder very quickly is whether there's algebraic structure on it. Okay? So what kind of algebraic structure do we have on this space sim, which so far is just a set? Kind of go up the curriculum of algebra, right? So first, linear algebra. Okay, so can we do linear algebra here? Is this a vector space? So being a vector space means that you can add things and you stay in here, you can subtract things and you stay in here, you can multiply by scalars and you stay in there. And all of these things work, right? This space is closed under addition, subtraction, and multiplying by scalars. So sim is a vector space over K. Okay. Okay, what's the next class that you take? Then you take group theory. So is this a group? So let's think about it. To have a group, you need to have an operation, which we tend to call multiplication. And I mean, I should say, whenever you have a vector space, you're a group under addition, right? You're a commutative group under addition. The interesting thing is if you're a group under multiplication. So is this a group under multiplication? No, why not? So once you have 0 in there, you're going to get into trouble. 0 has no inverse, right? Identity, the multiplicative identity should be the number 1, and 0 times x equals 1 has no solution. Okay? But even if you don't want to, if you don't want 0, the thing is that things here are not necessarily invertible, right? You can't take 1 over this and expect it to be a 1 over this is not a symmetric function according to the definition. So this is not a group, okay? Okay, so it's not a group. Then the next thing we might wonder is if it's a ring. So is this a ring? So to be a ring, you need to have addition. That's fine. Multiplication. You can multiply these things, and I think it's easy to believe that if you multiply two symmetric functions, you're going to be symmetric, right? And you need addition and multiplication to satisfy the axioms of associativity, distributivity, but I think all of that is easy to believe because we're just performing formal expressions on these polynomials. Okay? And so you can check all the details, but you'll quickly see that this is a ring. Okay? And well, if we have a vector space and we have a ring, then we know what to call that. That's called an algebra. So we learned at the beginning of this class. So sim was called a K algebra. And this is a good thing because remember that we're headed towards an object called the Hopf algebra of symmetric functions. Okay? And if we want a Hopf algebra of symmetric functions, we need something that is an algebra and a coalgebra. So we have the algebra part. Okay? Let me point out something else that's pretty easy, which is that this is a graded algebra. I think you don't have too much trouble believing that. So what degree would you call this? 2, and this, 2, and this, 3. And you can just grade this by degree. And if you multiply something of degree 3 by something of degree 5, you're going to get something of degree 8. So this is graded by degree. So remember that the way this works is that you grade homogeneous things. Right? So maybe I should say a little bit more about this, just to remind you that what this means is that sim is a direct sum of things of degree d over all the different degrees. And so what this means is that every element in the algebra of symmetric functions can be written uniquely as something of degree 0 plus something of degree 1, something of degree 2, etc. Okay. And actually, I'm realizing as I write this that I forgot to say something in the definition. Because remember that when you take a direct sum, that means you're only allowed finitely many summands. Right? And I meant to say that there. Otherwise, this equation would not be true. So a symmetric function has to have bounded degree. Okay? So it's a function which satisfies this property and has some bounded degree. Okay. So what I mean by that is that, so let's write another non-example. For example, if I take the sum over all degrees and then the sum over all variables of xi to the d, then each one of these individually is a symmetric function. But then you stop being a symmetric function when you add over all possible natural numbers, because now this is going to have infinite support in degree, and you don't want that. Is that last point clear? So you have to stop at a certain degree to be a symmetric function. Okay. Let's try to, before going into co-algebra, which we will go into, let's try to understand the algebra structure here. Okay? We have a k-algebra, and so we can ask, okay, do we have generators, do we have a basis, etc. Okay? So let me make a couple of definitions. A partition lambda is going to be a vector lambda of finite length, lambda 1, let's say, up to lambda L, where lambda 1 is greater than or equal to lambda 2, greater than or equal to, etc., up to lambda L, greater than or equal to 1, and these are integers. Okay? We call this a partition of n if the numbers add up to n. Okay? But I write this in a different color because sometimes we just write 4, 3, 1, 1 is a partition, and we don't say what it's a partition of. But yeah, so for example, 4, 3, 1, 1 is a partition the number 9. And I should say that we write 4, 3, 1, 1. This is the symbol for partition. And I should also say that sometimes we like to draw it like this. It's kind of a funny thing. It's a subject of very heated debate whether you should draw it like this, which is what's called the English way, or sometimes people flip it over, and that's called the French way. And sometimes people rotate it 45 degrees, and that's called the Russian way. And whenever you see a talk about this stuff, people will always draw it, and then they'll say, oh, I'm drawing it in the French way, and then half of the audience will scoff. I think nobody's ever going to agree on this, but I'm going to draw it in the English way, which is this. Okay? So 4, 3, 1, 1. Okay? Now, the point is that for each one of these things, I can define a monomial. Okay? So let's do that. So for example, what would be the monomial corresponding to 4, 3, 1, 1? We know what it is, right? Actually, do we know what it is? So okay, so if I give you 4, 3, 1, 1, then the monomial that you might define is maybe x1 to the 4th, x2 to the 3rd, x3 to the 1, x4 to the 1. Okay. We want to actually define a symmetric function, and so what we do is we just do that, and then we symmetrize. So we permute the variables in all possible ways. Okay, so what we do is that we sum over all the different permutations alpha of lambda, and we just do x to the alpha. Okay. This is called the monomial symmetric function. And these are okay, so maybe first I'll write an example. So M4, 2, 1, 1, what is this? It's the sum of xa to the 4, xb to the 2, xc to the 1, xd to the 1, where a, b, c, and d are different. And actually, you see the reason that I say different permutations is that you might think of we're taking the vector 4, 2, 1, 1 and permuting it in all possible ways. So if you switch the two ones, is that considered a different permutation or not? It's the same permutation, and so actually I should say that C is less than D. So let me maybe make a smaller example to illustrate this. So what is M11? I'm looking at summing over, let's say, xa to the 1, xb to the 1, right? And I take all the possible permutations of the exponents 1 and 1, okay? But the thing is that if I were to write this and sum over a different from b, then what would be the coefficient of, like, x1, x2? The coefficient would be 2 because it would appear as x1, x2 and as x2, x1. But I'm not considering those to be different permutations, and so that's why I actually have to say that a is less than b to get this right. Okay. So the monomial symmetric function, these are kind of the smallest possible symmetric functions in that once you write one monomial, like x1 to the 4th, x3 squared, x7, x8. Once you write that monomial, if you want to be symmetric, you have to contain all the monomials which have those exponents, and so that's called the monomial symmetric function. Okay, these are kind of the smallest things you can write. Okay? Now, so maybe I'll write this here. And then the claim that I want to make, one of these claims that in a book they would say this is obvious, and you need to think about it for a little bit maybe. The claim is that all of these guys form a basis for the vector space of symmetric functions. And let me say it a little bit more finely. If I take the monomial symmetric functions such that lambda is a partition of n, or let's say d, so that it sounds like a degree, then this is a basis for the symmetric functions of homogeneous degree d. Okay? Yeah?
Regarding that last point, the coefficient 2, the second example, is redundant. Because 2 is not equal to 3, but 3 is also not equal to 2.
That's right. So you're right that when I wrote here I different from j, xi, xj, then I'm actually counting these twice. So really what I meant to write is I less than j here. And then we get the 2 in front. Okay? So, for example, what is this? This is a good example. So here is something of degree 2. Okay? So I'm claiming that the monomial symmetric functions form a basis for this. Okay? So how can I express this symmetric function in terms of the monomial ones? Well, the way you do this is you just kind of look at all the monomials that appear, and then recognize that the different summands have to be monomial symmetric functions because they cannot be anything else. Right? Once you have one monomial, you have to have all the symmetric ones. Okay? So for example, when I write this guy, what am I going to get? I'm going to get, this is which monomial symmetric function? This is M2, right? And what's this one? Well, it's 2 times M1. Okay? And really, this is one of these proofs that if I try to write something down, I'm just going to confuse you. So the proof is going to be just stare at it, and I think you'll convince yourself that it's actually a fairly obvious statement. So we'll put in quotations obvious, but you know whenever we say obvious, we mean meditate on it for a little bit, and then you'll see that it makes sense. Okay? Okay, so we have a basis for these guys. Now, let me now define a different basis. And you'll see in a second why I want to define a different basis. So again, for a partition lambda, I'm going to define a different symmetric function, which I'm going to call E lambda. And this one is going to be called the elementary symmetric function. Lambda is going to be a vector. Lambda 1, lambda 2, etc. And E lambda is just going to be the product of E lambda 1, E lambda 2, up to E lambda L, where these are numbers. Okay? And so I have to define what E sub number equals. So let me just say that E sub D, where D is some number, is going to be the sum over I1 less than dot 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 less than ID of E I1 dot 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 E ID. You might recognize this as a monomial symmetric function. Sorry, I mean X here. So let's do an example. E3 is going to be the sum of I less than j less than k of xi, xj, xk. Okay? And so these are just all the different triple products among all your variables. You have x2, x5, x7, x8, x10, x100, etc. Okay? So do you recognize this as a monomial symmetric function? For example, this one right here is E2, right? Sum over I less than B of xa xb. And so what is this one? M 1, 1, 1, 1, 1, 1, 1, D times. So M 1, 1, 1, 1, 1, D times. Okay?
So would that be the proper way to write it, or is there more? How do we write it just in a shortcut of the formal manner?
How do I write this?
Is that?
You don't like this?
No, I mean, it just looks a little, odd.
Yeah, so sometimes people write M sub 1 to the D. You know how it is. When I teach, I try to be as clear as possible, and then in books they might try to be a little bit more pedantic. So maybe, yeah. In books sometimes they come up with a notation where this partition is labeled 1 to the D. But I think this is clear. ED is pretty clear too. Yeah. Okay, so these are the elementary symmetric functions. I should say that I heard somebody say here MD instead of M1111, and if you, instead of defining this, you would have put MD here, then you would get a different basis, which is called the power symmetric function, which is also very important. But let's talk about the elementary symmetric functions. Okay. So I am okay. Before proving anything, let's do another example. So what about E21? What is this? Let's compute E21. So by definition, okay, this is another tricky thing. Is this 21 or 21? We get lazy and we don't write parentheses and commas, and generally whenever we do examples in combinatorics, the numbers are less than 10. Okay, so just kind of get used to that. This is meant to be 2, 1, and so E sub 2, 1 should be E2, E1. Okay. E2, E1. And we know what each one of these things is. So the first one is sum over I less than j of xi xj. And the second one is the sum over k of xk. Okay. So what is this going to equal? Let's try to write it. Given that we have a basis for our space, let's try to write it in terms of that basis. So how can we write this in terms of in terms of monomial symmetric functions? We just multiply this times this. So what kinds of terms do we get? Well, there's two kinds of terms that you can get. You can get xi times xj times xk, where the three variables are different from each other. Or you can have it happen that k is actually one of these variables. So that means that the kinds of terms that you get are this kind of term and this kind of term. This is xi squared xj. So why did I write xi squared xj? Because one of the terms that appear here is xi. Okay? And so when I multiply xi xj times xi, I get xi squared xj. Okay? And I differ from j, which means that xi xj squared also appears here. Okay? Now what about this term here? Does this look good to you guys? Does it have to be? Or do I have a coefficient in front here? How many ways are there of getting the product xi, xj, xk? Out of this. Maybe it's easier if I call it xa, xb, xc. So how can you get xa, xb, xc here? You can either get it by having xa, xb times xc, xa, xc times xb, or xb, xc times xa. So that product actually appears 3 times. Okay. So this is 3m 111 plus m21. So let's think about that. Why don't I have a coefficient here? Because how can I get an xi squared xj? Actually, the only way I can get it is by putting xi, xj here and xi here.
Why didn't you obtain xi, xj squared?
And so, right, so we do obtain an xi, xj squared, and the thing is that here I'm summing over all I different from j. And so that means that here, xi, xj squared is also hiding. I didn't write it, but it's also in there. Okay. And so this is how you write E21 in terms of monomials. Okay. Now let me just write down some formulas for you. For example, in degree 3. In degree 3, I have 3 different partitions of the number 3. 1 plus 1 plus 1, 2 plus 1, or 3. And so I get 3 elementary symmetric functions, and each one I can write in terms of the m's. Okay? And so when I do that, I get the following expressions. I get m3 plus 3m21 plus... You have to do this by hand or by computer, but you have to do it, right? I mean, you have to do computations like this. I'm just showing you what you get when you do it. This is what you get in degree 3. What does that imply about the 3 e's? There are bases. Why? Because the matrix representing the e's in terms of the m's is upper triangular and therefore invertible. Right? And so if I can write the e's in terms of the m's with an upper triangular matrix, then by inverting that matrix, I'm going to be able to write the m's in terms of the e's. And this is not an accident. This happens for every degree. Okay? So let me make a lemma that the transition matrix that writes the e's in terms of the m's is upper triangular. And actually with ones on the diagonal. You might know Do you know what it means to have ones on the diagonal? It means that not only is it invertible, but when you invert it, you still get integer coefficients. Right, because the determinant of this matrix is 1. If it's upper triangular and along the diagonal you only have ones, the determinant is 1. And therefore, when you invert the matrix, everything is going to be an integer. Okay? Like Kramer's rule or whatever rule you like to use for inverting matrices. And so that means that not only are E and M bases, but they're kind of integer bases. Okay? But anyway, so let me write the corollary. So the corollary here, and okay, so this requires a proof, right? And I should say that I'm just not going to do the proof. Okay? This would take us into a little bit deeper into the combinatorics of symmetric functions, which I'm happy to show you in office hours or any other time, but I'm trying against my will to stay on point and talk about and not go too deeply into the combinatorics of this and to focus on the Hopf algebra structure. But okay, so proof. Let me, for example, refer you to Stanley's book on enumerative combinatorics. And I'll tell you what, the other thing that we should do is take this to the forum. I think this is a good thing to discuss in the forum. Whoever is interested, maybe we can together write down a proof of this. One thing you should realize that's interesting is that to decide if this matrix is going to be over triangular, you have to decide what order to write the rows and columns in, which I prepared class, and so I did it very smoothly, and it looks upper triangular. But if I hadn't prepared class, I would have put the order 1, 1, 1, 2, 1, 3. Give me just a second. 1, 1, 1, 2, 1, 3. That's a more natural order, just to use the same order for rows and columns. And if I were to do that, this wouldn't have worked. So actually, it is non-trivial to figure out, given this order, if I write these in a certain order, what order should I write these in? It's not trivial, and it's an interesting combinatorics problem, which, again, I'm happy to discuss in the forum. You had a question, Krista.
Yeah. So you gave us the basis, and then we used linear algebra and said, okay, we have another basis, but we're still trying to talk about the algebra. So what's so special? Okay, we have two bases, and what does that say about our algebra?
That's a great question. So why are we talking about bases which are only linear algebra when we actually want to talk about algebra here, right? And I think that's a very good question. So far, let me just write down the linear algebra statement, and then I'll go to your point, and then I'll take your question in you. But let me write corollary is that I have a second basis. Sorry, E lambda, such that lambda is a partition of D is also a basis for the symmetric functions of degree D. Okay. That's a corollary of this and some basic linear algebra. You had a question, Nino?
So this is just, this might be a little digression, but I was noticing that the coefficients for this, coefficients along the m sub 3, m sub 2, 1, they're triangular. Does it always come out this nicely in patterns?
Oh, I see.
For degree 4, we would have 1, 3, 6, and 10, or is it just particular?
Yeah, so Nino's question is, I know these numbers and they're so nice, and is it always this nice, right? Because these are precisely the triangular numbers 1, 3, and 6. If you know what triangular numbers mean. Triangular numbers are n times n plus 1 over 2. I really like that you have this instinct that when you see a number, you want to know what it counts. Is it a triangular number? What is it? It's a good instinct to have in combinatorics, and in combinatorics, we do have an answer for if you point to a given number here, what does it count? We know what it counts, and the answer is not the triangular numbers. But it's something else that, again, I'm happy to tell you after class. Okay, E lambdas are a basis for sim D. And now to answer Krista's question, let me show you a corollary, which is that E1, E2, E3, etc. Are actually, let me say it even a little bit more strongly than this. So let me say that the algebra of symmetric functions, sim, is generated by the elements E1, E2, E3, etc. That's the first half of a statement that I'm going to make. Can you see why sim is generated by these guys? Now here I have E sub numbers, not E sub partitions. But the thing is that I'm saying that these things are a basis for sim D, meaning that every symmetric function can be written in terms of the E lambdas as a linear sum. Every symmetric function is a linear sum of E lambdas, but by definition, E lambda is a product of E sub numbers. Okay? So if every symmetric function is a sum of E sub lambdas, that means that it is a polynomial in E sub numbers. Okay? And so this is actually a generating set as a ring. And that is why we bother with this different basis, because the other basis didn't buy us this. Right? It was not true that M sub lambda was a product of smaller things. But the fact that these E sub lambdas are products of E1, E2, E3, etc. means that you only need E1, E2, E3, etc. to generate all the E sub lambdas and therefore to generate the whole ring. Okay? So sim is generated by these guys, and not only that, it's generated freely commutatively. In other words, sim is precisely equal to the polynomials in these variables. So here I can actually write a sketch of a proof. So proof generating is what I just said. Okay, so follows from the corollary. The fact that these guys generate follows from the corollary. Now, what we need to show is that they generate freely commutatively. Okay? In other words, what I need to show is that the only relations between the EIs is that they commute. Now, it is clear that the EIs commute because here we're just dealing with polynomials, right? So EI is some polynomial, EJ is some polynomial. When you multiply them, that's commutative. Okay? But the question is, why are there no other relations between the E's? So let me make that argument. If I had a relation among the E's, so I don't know, let's say that the relation looks like E4, E3 is equal to E5, E1 squared. I'm making something up. Minus 2 E2 cubed E1 plus E7. Okay. If you had a relation like this, then multiplication would not be free, because there would be two different ways of expressing E4, E3. You could express it like this, or you could express it like this. Being free means precisely that you cannot have relations like this. How do I know that I cannot have a relation like this? If I had a relation like this, Then what's wrong with that?
Create a relation on the ends.
Then the thing is that we actually have names for these things. So what is E4, E3 called? According to that, this is just called E43. This one is called E sub 511. This one is called E sub 2221. And this one is called E7. And so I have created a linear relation among the E lambdas, which cannot be because the E lambdas are a linear basis. Contradicting this thing here. Okay? And that's the end of the proof. So we get this kind of cheap, actually. Because we do the linear algebra at this level, we actually get a free generating set in the algebra level. Okay? And this is why it's worthwhile to talk about the second basis E. I mean, you might think, okay, we already had a basis. Why do you need another one? This basis is very natural, but it doesn't give us that theorem. Okay? And that means that we fully understand the algebra of symmetric functions. It has these generators, and the only relations are that the generators commute. Okay? Now, I hope you're making the connection between this and how I started the class talking about the algebra of breaking sticks. Because that algebra was generated by a stick of length 1, a stick of length 2, a stick of length 3. And the product was free commutative. Okay? And so what I just showed is that the algebra of symmetric functions as an algebra is isomorphic to the algebra of breaking sticks. Okay? As an algebra so far. Now we're headed to an equality of Hopf algebras, and this is the first step. Okay. Are there any questions about this? Yep.
We should make that statement more explicit, because when I look at E sub 2, I look over here and say E sub 2 is X sub 1, X sub 2. Like, I don't see the relationship between the sticks and the E's.
So let me say more explicitly that, okay, so I have two algebras. The algebra of breaking sticks and the algebra of symmetric functions. And I claim that they're isomorphic. And the isomorphism takes the stick of length 5 and maps it to the symmetric function E5, which is this weird thing. So the isomorphism actually is quite non-trivial. You take a stick and you do something non-trivial to it. But this theorem shows that is an isomorphism. Okay? So you're justified in thinking that it's surprising, because this I think sounds like a much more complicated algebra than just breaking sticks. But it turns out that as an algebra, it's not more complicated. Okay. So let's go now to the coproduct, because we want to do Hopf algebras here. So we're going to define a coproduct on symmetric functions so that we can get a Hopf algebra out of it. Okay? And the usual thing, I'm actually going to kind of do two things. I'm going to think something, and I'm going to say something different. Okay? So what I'm going to think is that the coproduct of a function, so this is a symmetric function in infinitely many variables, and what I'm going to think is that I'm just going to plug in two different, so you can think of this as the variables you can think of as an alphabet. Okay, the alphabet is x1, x2, x3, those are your letters. The coproduct, I'm just going to think of this as taking the function and plugging in two alphabets. Okay? So you take variables x1, x2, etc., y1, y2, etc., and you plug that into your function. Okay, and this is going to be the informal way of thinking about the coproduct. But that doesn't really make sense as a definition, because you know that the coproduct needs to map symmetric functions to symmetric functions tensor symmetric functions. And so let's write down a little bit more precisely what I mean here. So what I mean is the following. So if I have some function of x1, x2, etc., and this is symmetric, now let's plug in consider a new set of variables, y1, y2, etc., and plug in f of x comma y. Okay, and I'm going to do an example of this in a second. In fact, I think maybe we should just do one now so that you see what I'm talking about. So let's do an example here. So let's say that my function is the monomial symmetric function m21. Okay? So I want to figure out what this is. And so what I'm saying is plug in x and y. Okay? So what happens when I do this? I'm going to do the monomial symmetric function, but I have two kinds of variables now. Ones are called x's, the other ones are called y's. Okay? And so let me think of of z as being the x variables, comma, the y variables. So m21 of z is just by definition sum for I different from j of zi squared zj. Okay? Where I'm letting the z's vary over all the x's and y's. Okay? Now, okay, so imagine this is really x1, x2, etc., and then y1, y2, etc. So how can you make a zi squared zj? You can make it in several ways. You can make it, for example, by using xi squared xj, or you can do y squared yj, or you can do xi squared yj, or yi squared xj. Yeah? These are all the ways of making something squared something here. So you get four kinds of things. Either you use two letters x, you use two letters y, you use one of the letters in x and one of the letters in y, or the other way around. One of the letters in y and one of the letters in x. Okay? So should I say that I and j are different here, or should I not say that? I mean mathematically wise. Can you get the term xi squared yi here? So I see some of you saying yes, some of you saying no. Xi squared is, xi is over here, yi is over here. They're different variables, even if they have the same index. They're different variables. And so they can appear as something squared something. Okay? And so here, I don't need I and j to be different from each other. Okay? I and j could be equal, and I and j could be equal here also. Okay? So this is what I mean when I say plug in two alphabets, x and y. And so what you're going to get is some expression in x's and y's. And so what I'm going to do now is write this in kind of sweeter notation. Separate the terms into x's and y's. Okay? So let me continue the computation here. I'm going to take each one of these terms and separate the x's from the y's. Okay? So what do I get? I get some I different from j, xi squared xj. That's the x part. And the y part is 1. Plus. The second term has nothing in the x's, and it has this in the y's. Okay? The third term has this in the x's, and this in the y's. And the last term has this in the, maybe just to be consistent with the letters I used there, I'll write it like this in the x's, and this in the y's. Okay? And so by that sum, I mean doing this. Then what should I define the coproduct? The coproduct of f is going to be just making this into a tensor. Sum of f1 tensor f2. Okay? So in other words, what is delta of m21 according to this formula that I wrote here? Let's write it over here. Well, maybe let me not try to squeeze it in here. Let's actually clean this up a little bit. So this expression right here is m21 in the x's, right? Times 1 in the y's. Plus 1 in the x's times m21 in the y's. Plus m2 in the x's times m1 in the y's. Plus m1 in the x's times m2 in the y's. Okay? And so given this, what should I define delta of m21 to be? Well, it should be m21 tensor 1 plus 1 tensor m21 plus m2 tensor m1 plus m1 tensor m2. Okay? So it's kind of a strange way of defining a coproduct, especially when you carrying out the computations is a little bit tricky. And I wanted to do it, so you see, I want to stay honest. This is not so easy to compute. But this is the definition of the coproduct. Okay, now my definition is complete. And hopefully you see why this is really how I want to think about this in my head. Okay? I mean, you can write it out, and it's kind of messy. But in your head, really, you should just think you're plugging in two sets of variables. Then, for example, how do you know that this thing is going to be co-associative? What does it mean to take delta of delta? If delta takes your alphabet x and now puts two alphabets x and y, then what should co-associativity do? If you do delta of delta, presumably it's going to take x and now plug in 3 alphabets instead of 2. And so you actually can just write delta squared of f of x is just going to be f of x, y, z in your head. You can kind of think that, and then, okay, there's some ugly formulas that go with it, but that's the intuition of why this is actually a proper coproduct. Okay? Let me okay, so I define a coproduct, and then let me make a proposition. Which is that delta of En is what? Well, we're trying to show that this is the rock breaking Hopf algebra.
What is E0?
E0 is 1. That's right. Yeah. So proposition is that this is true. Okay? Corollary, if we have the rock-breaking Hopf algebra and the Hopf algebra symmetric functions, as algebras they agree. And here I'm showing that that map that takes the segment of length Li to the elementary symmetric function Ei is also a coalgebra homomorphism. Therefore, this is precisely an isomorphism. Okay. Corollary is that H is actually isomorphic to Sim. Okay, and this is the main result that I was mentioning to you. That the Hopf algebra of breaking rocks is isomorphic to the Hopf algebra of symmetric functions. Hopefully now you see that this is not meant to be a trivial statement. It's actually is, even though it's a corollary, let's call it a theorem because it's a very interesting statement, very non-trivial statement, that this Hopf algebra structure on symmetric functions, which again in principle